Hi, this is Dongwei and Samer El Haj Mahmoud from ARM. Today we're going to be talking about ARM SystemReady and the UEFI ecosystem for firmware. So I will be talking about the ARM SystemReady program a little bit, and then Samer is going to take over and talk about the UEFI firmware ecosystem. The ARM SystemReady program is a newly launched program from ARM with the intention to get the software just run on ARM-based devices. And we extended this success of the ARM server-ready program to the embedded edge and IoT space. If you're familiar with the ARM server-ready program that we launched 2 years ago, basically to set up the system, we are trying to make what we call the ARM servers boring, which means that we want to establish sufficient amount of hardware and firmware standardization so that the operating systems and hypervisors can just run on these ARM-based servers. In the server space, we originally established two specifications. One is what we call the server-based system architecture, SBSA, which established the hardware requirements for the generic off-the-shelf OSs to just install and run. And then we also established the firmware requirements in the specification called SBBR, the server-based boot requirements. This is where we established the firmware requirements in terms of UEFI, ACPI, and SMBIOS on top of some of the ARM-specific interfaces to enable the generic operating system to be able to run. And to check against these the compliances to these specifications, we also produce what we call the Architectural Compliance Suites, ACS, so that we can run these test suites on top of the silicon providers' reference systems as well as OEM, ODM products to check against the compliance to these specifications. And you can see the URL linked to the program that we launched 2 years ago. And this year, in October, we launched the ARM SystemReady. So basically, we moved the learnings that we had for the server-ready, and then we extend that into the edge and IoT space. So borrowing the same success, the same arrangement that we had in the SystemReady, we also have two specifications. One is the hardware requirements. So in hardware requirements, we have established the base system architecture, the BSA, to document the minimum set of hardware requirements for the OSs and hypervisors to be able to install and run. And in addition to that, we also enable the structure where we can add segment-specific extensions for the hardware requirements. For example, for servers, we have the server supplement for the BSA document to address the server requirements. And of course, for other segments, we can in the future develop specifications to cover the requirements there too. And then for the firmware side, we leverage the SBBR document that we had before in server space. We extend that to cover the other segments as well. And we have this document called the base boot requirements. And in the document, we expand and include many of the common interfaces for firmware. And then we also recognize different operating systems and hypervisors may have different requirements in terms of what the firmware interfaces would look like. So we also allow the flexibility. We arrange different recipes for different operating systems. And of course, we also have the certification requirements that we produced, and then we also extend the architecture compliance suite to cover the newly developed BSA and BBR specifications. So the work for the ACS for SystemReady is work in progress. We have this the test suite for the server side, server-ready side, but we are extending that to cover the different bands that we are calling them, and to cover the different segments and different OSs. So the base boot requirements, so we're talking about the firmware requirements, right? So on the left-hand side, we listed the different interfaces that we use inside of the base boot requirements. So the PSCI and SMCCC are the interfaces that we develop for the ARM-based devices. These are ARM-specific. On top of that, we add the requirements for UEFI, ACPI, and SMBIOS, as well as device tree. And then we specify, which of these interfaces are used in different recipes. So in the middle part of this slide, I show the different recipes that we have created so far. For SBBR, this is originally developed for the server space, but in fact, these are not just for the server devices. It could also apply to the edge devices and IoT devices as well. It is really operating system specific. So in this recipe, we require the use of PSCI, SMCCC, UEFI, ACPI, and SMBIOS. But for some of the other operating systems, they may not need to have the ACPI interface. So we have the EBBR recipe, which is developed based on the EBBR specification, and it is developed to meet some of the devices that would not need to have ACPI. In addition to that, we have another recipe called LBBR, which actually replaces the UEFI requirements for the servers with the Linux boot firmware. So you can put a Linux boot firmware into your system and be qualified to this LBBR recipe and still meet the requirements for some of the OSs that the hyperscalers are enabling. In addition to these specifications, we also developed the BBSR, the base boot security requirement document for the secure boot and firmware update interfaces that are utilizing the UEFI interfaces. And as I mentioned, the EBBR document is actually a separate specification that we have been developing with the community. In terms of the landscape, the reason why we are creating these different recipes, this can be shown in this picture. So in the middle part of the slide is where we use the SBBR recipe to address. These are the spaces where it's either servers or other devices that are typically developed in the more horizontal environment where the OS vendors don't necessarily develop the hardware, right? So there are different partners doing different parts of the ecosystem, from hardware, firmware to operating systems. So SBBR can be used to satisfy a lot of these popular operating systems like Microsoft Windows, Red Hat, VMware, and many of the Linux favorites as well. You have AWS and Oracle Linux. Also, many of the Linux distros can also support SBBR. These are like Ubuntu, Fedora, SUSE, Debian, and many of the BSD distros as well. But there are a lot of devices that are supporting EBBR without ACPI, and these systems typically support device tree as the interface to report the hardware on the system. And many of the operating systems like Ubuntu, Fedora, SUSE, Debian, and many of the BSD distros, they can support that as well. And also some of the customized Linux, embedded Linux as well. These are typically supported in the more vertically developed environment where the device vendors also develop the operating system. But being able to support the eBBR recipe allows you to also support the generic OSs like Ubuntu, Debian, SUSE, Fedora, and so on. On the right-hand side, you also get some of the hyperscalers interested in using the Linux boot as the firmware. So we created LBBR for that. And with these recipes and with the hardware specifications, we created this SystemReady program with multiple bands. So if you're developing servers, you basically have two choices. You either use the SBBR firmware recipe, or you use the LBBR recipe for the firmware. But the hardware requirements are the same based on the BSA and then the server supplement called the SBSA, sorry. And then if you're developing the edge and IoT devices, again, you have two choices depending on which operating systems you want to support. The SystemReady ES is where you still use the SBBR firmware recipe, and your hardware would look to comply to the BSA. These are used typically to support the OSs like Red Hat, Rio, VMware, and Microsoft Windows. But also, we created the band called SystemReady IR. In this case, you don't have to support ACPI. You typically support device tree, and then you use the eBBR recipe for the firmware, and then you support the OSs that I touched upon earlier on the left-hand side, last page, right? We also created a pre-silicon program to help the silicon providers to make sure their silicon can be designed to be BSA compliant. And then we also produced the security option for people who can have the firmware interfaces comply with the BBSR documents to supply the secure boot and firmware update interfaces. Then they can have the option for this security certification. So these are the nice looking stamps that we have for each of the different bands, and also the options that I just talked about. So for systems that can be certified, you will receive these stamps after the devices are certified. So these are a little bit of more details on what each of the bands are requiring the developers to come up with. So, like I mentioned, on the server side, for both the LS band and SR band, you need to have your hardware to be BSA plus SBSA compliant, and then the firmware can be different. On the server-ready SR side, on the right-hand side, you would have the firmware to meet the SBBR requirements, the recipe requirements. On the left-hand side, for the LS band, you use Linux boot. And then if you're developing IoT or edge devices, then you're going to be interested in the middle two bands. And again, the hardware would be very similar. It is BSA compliant. And then for firmware, it depends on which operating system you want to support. If you support the operating systems that want to have ACPI, then you want to meet the requirements for the ES band. And if you don't have to support these OSs, then you can support the IR band by not using the ACPI. So typically, for a lot of the devices are using U-boot to support the UEFI interfaces and device tree to make the devices to be IR compliant. And then for the devices that are supporting Windows, VMware, and Rail, typically people use EDK2 open source project to develop the firmware, and then that would realize the necessary UEFI CPI interfaces. But that's just a typical implementation. We have examples actually with people using U-boot to support the ES band as well, adding the support of ACPI. And the benefit of the IR, ES, and SR band is that all of these bands are using UEFI interfaces, and so you can use the same kind of OS bootloader to separate from the hardware development, right? Like the loaders like Grub. And also for these 3 bands, you can support the UEFI secure boot and firmware updates with the capsule services. So in terms of architectural compliance suite, like I mentioned, we already have the ACS 3.0 available, which can be used to certify devices for the SR band. We are developing the ACS for the other bands as well, but today we can actually use the ACS 3.0 SPSA level 3 package to certify ES, because ES is actually very similar to SR. Okay, so at this point, I will hand over to Samer to talk about the ARM open source firmware efforts.
All right, thank you, Dong. For my part of the slides, I'm going to go over the ARM open source firmware and demonstrate some examples of open source firmware implementations that are ARM SystemReady compliant. We'll start by saying that within the ARM ecosystem, firmware solutions come in different shapes and forms and different projects, different boot models. Some are open source, some are commercial. ARM's strategy in general is to encourage partners to provide the open source implementations for any of these different boot models. And examples are the projects that I have listed here on this slide: ARM Trusted Firmware, the Tiano Core EDK2 project, U-boot, and of course Linux boot, and the OpenBMC project for BMC firmware. Let's talk quickly about these projects. The first one is the Trusted Firmware. Trusted Firmware is an open source, open governance community project. It has the reference implementation for the secure world firmware for ARM systems. The TFA project specifically under Trusted Firmware has the reference implementation for all the ARM Cortex-A and Neoverse processors across the different market segments. It's a very active community-driven project with a growing number of platform ports and vendors that are either supporting or participating and contributing upstream code to the repository. In all of these slides, you'll find links to these various software projects if you want to check them out. The next project is the Tiano Core EDK2. Again, that's the community project, open source, with the implementation of UEFI standards. That includes the UEFI specification itself, but other specifications from the UEFI forum, such as the ACPI and the platform initialization, the PI, DXI specification, and even the UEFI shell. And many of these standards are foundational components to the ARM SBBR requirements in the ARM-based boot requirements specification that Dong talked about. As you see on the slide, there is a growing number of partners and community members that are participating in this project in the ARM from the ARM ecosystem as maintainers, code contributors, reviewers. Many of these have complete or partial platform ports or specific silicon drivers and libraries and support code, mostly in open source under the EDK2 platforms repository. There is also the EDK2 nano-OSI, which does contain some binaries that are redistributed to go along with the rest of the firmware. And finally, there is the UEFI SCT project under the Tiano Core community project. And UEFI SCT is the self-certification test. It's part of the test suite that partners or implementations can run on their own to validate the implementation is compliant with the UEFI specification. And it is worth to note that the UEFI SCT is also part of the ARM architecture compliance suite, the ACS, that Don talked about. And ARM is contributing code fixes and being one of the maintainers for this project. The next project I would like to talk about is U-Boot, or the Universal Bootloader. It's an open source firmware that includes support for multiple architectures, including, of course, ARM support. It's easy to port and debug. It's widely available. Many devices, especially around the embedded and edge and single board computer devices, which are mostly a vertically integrated ecosystem. Many of these devices use U-Boot as the main firmware and bootloader. U-Boot does have a UEFI layer implementation that implements the ARM EBBR specification, or the embedded base boot requirements. The UEFI layer that's presented by that implementation allows for standard OS bootloaders like Grub to load and boot a standard OS, thus helping in realizing the vision of SystemReady for this class of devices using this firmware. There is ongoing work to verify the compliance of that implementation with the UEFI specification and with the ARM EBBR specification using the UEFI SCT test kit. That is a work in progress, and there's a lot of activity happening now on upstream to report issues and contribute patches and fixes to the code to complete its compliance. The documentation link is also available if you'd like to learn more about the UEFI layer in the U-Boot project. The next project I would like to talk about is Linux Boot. So Linux Boot, again, as Dong mentioned, is an alternative firmware stack implementation that's used mainly by some of the hyperscale data centers on servers running in these data centers. It relies on using the kernel, the Linux kernel, as the normal world firmware. It can provide different boot chaining methods of how it can be loaded, or how it can load the next stage up to the final OS. The idea is to reuse existing Linux drivers without having to write separate drivers for the firmware for UEFI or Dixie. On ARM specifically, one of the advantages of Linux Boot, or one of the possible implementations, is to completely bypass the PI implementation that is the foundation for UEFI, and you can load Linux Boot directly from the trusted firmware, and then from Linux Boot directly to the guest OS. Although there is ongoing work led by Google and Facebook to implement a UEFI ABI on top of Linux Boot in an approach similar to how U-Boot implements UEFI API without relying on PI and Dixie. If you are interested in this work, you can join the OSFC Slack server EFI boot support channel, where this discussion and work is happening. OpenBMC is a BMC firmware project that it has the sample implementation for servers. ARM does have a specification called the Server-Based Manageability Requirements, or SBMR. The SBMR specification standardizes BMC interfaces for ARM servers, including relying on many industry standards, including IPMI and DMTF, Redfish, and MCTP, and other standards from DMTF and other standards bodies. The OpenBMC does provide a way to implement the SBMR specification for ARM servers. ARM does participate in the OpenBMC project as a member of the Technical Steering Committee, but also we have ARM partners like Ampere Computing that are in the process of upstreaming their BMC firmware support for their platforms to the OpenBMC project. In this next set of slides, we are going to showcase some of the ARM SystemReady certified systems, or systems that are in the process of getting certified, and show how that relates to the open source firmware projects that we just talked about. The first is the Ampere Ultra Mount J 2-socket rack server. This is an ARM SystemReady SR certified, so it's a server, so it's part of the server band. And in the past, Ampere has been a partner that's certified also with ARM Server Ready. So this new generation of CPU and system reference system is certified as with the SystemReady SR 2.0. The Ampere Ultra Mount Jade is a choice for evaluating ARM compute and enterprise servers. It's a cloud-native, high-performance, scalable CPU. Ampere offers firmware options that include both open source and commercial firmware for both the UEFI and the BMC. Commercial firmware is from EMI for UEFI and the BMC. The open source firmware is available today. You can check it out, the EDK2 platforms code, as well as the OpenBMC code that is SBMR compliant on the Ampere GitHub. There is also support that is a work in progress, and some of it is already available upstream for the Linux boot firmware on these servers. The upstreaming for the EDK2 and OpenBMC is work in progress, but you can review the code and see Ampere's participating in the Tiano Core and OpenBMC projects. The next platform we'll talk about is the Raspberry Pi 4. The Raspberry Pi is an ARM SystemReady ES certified. It can be used as an IoT system, as an edge gateway, even as a developer box, a low-end developer box. The Raspberry Pi is a very popular box. It's very affordable. It's being developed, the firmware is being developed as a fully open source project supported by the community, with leadership provided from VMware, ARM, and Accu Consulting, and others in the community that have ported the code over the years from Raspberry Pi 3 and now to Raspberry Pi 4, and made it available under a project on GitHub called PFTF, or Pi Firmware Task Force. The code is also fully upstreamed to Tiano Core, EDK2, and to the Trusted Firmware projects. And there is a Discord community channel under the ARM ecosystem Discord server that you are free to click on the link here in these slides and join the discussion and the direct contact with the community that's behind the project, as well as check out the blog webpage for the project that includes a feature tracker and issue tracker and different tutorials and other guides. The next system I'm going to talk about is the NXP Layerscape 2160 Reference Design Board, or RDB. This system is now ARM SystemReady ES certified. This is a higher end embedded edge server gateway, can be used for network function virtualization and 5G switching and other use cases. It's a reference design that OEMs and ODMs can use to build their own systems using that NXP 2160A SoC. The UEFI code is available both upstream and from NXP. The upstream code is already in Tiano Core, as you can see from the link in this slide. The NXP code is available on Code Aurora and may include some additional code that's still in the process of being upstreamed. Trusted firmware code is also available on Code Aurora from NXP, and upstreaming is work in progress. And you can check out the web page and the reference designs and other documentations on the NXP website. Next is the Solid Run Honeycomb LX2K workstation. It's in the process of being ARM SystemReady ES certified. It is a system by Solid Run that is based on the NXP Layerscape 2160. It can operate in any of those roles that the 2160 is targeting, as well as being a microserver or a workstation in a mini ATX chassis. The code is available open source on the Solid Run GitHub repositories, both the UEFI and the trusted firmware code, along with a nice script to easily resolve all the dependencies and tools and build the entire firmware image. There is also a Discord community channel for the discussions and to get contact with the developers from Solid Run, and the upstreaming is also work in progress. And finally, the last system that I will showcase here is the NXP Layerscape 1046 Freeway, as well as the reference design board, the RDB. These systems are going through the ARM SystemReady ES certification. They include processors and a form factor that's suitable for high-performance IoT, edge gateway, access points, and other roles. You can see the code is already in the process of being upstreamed. Some of it is already there in the Tiano Core project, as well as a more complete code that's still being upstreamed in Code Aurora for both the UEFI and the trusted firmware projects. And you can check out the reference designs and documentations on the NXP webpage. That's all what we had today. Hope that you enjoyed this presentation about ARM SystemReady and the open source firmware ecosystem. Thank you.